Okay, then you can review later on. All right. Okay, so before we go through the concept of frequency hopping, let's understand a little bit about the impairment of the wireless communication. Okay, for wireless communication and the system, how does it work? How many components are there? So actually it's the same as the general communication. In general communication, if you go back to previous handout, you will see that, okay, I mentioned a lot about transmitter, right? The channel and the receiver. So whatever communication type you use, what I mean is whether it's wired or wireless. So the system should have at least 3 components, okay? So input go to the transmitter. Input means the information that you want to send. In terms of IoT information, it may be the information from sensor or actuator. And if you use the wireless protocol, whatever standard is, it may be Wi-Fi using Raspberry Pi or Zigbee, right? So this one is the communication. It communicates wirelessly to transmitter to the channel through the receiver. Okay, so at least 3 main components should have in the system. Okay, so and this slide show not only just transmitter, receiver, and there are 2 transmitter here. This slide show the things we call impairments of the propagation channel. Okay, so as I mentioned that by using modern modules for IoT application, most of the technology use the wireless protocol, right? Then you have to understand the technique behind to improve the quality of the signal. Okay, so to improve the quality of signal means that the system may the signal within that system may degrade with some reason. Okay, so this is a kind of problem of the wireless propagation. Okay, you may observe the words of attenuation. Okay, I try to change the color. Okay, you may observe here, it is attenuation, it is multipart, and it is interference, and also it is the interception. Okay, you have to understand every impairment, and then you can, as an engineer, if you know the problem, then you can select the suitable technique that can help your system improve, right? Okay, so please take a look for each impairment of the propagation channel. For the attenuation, what is it? You know the words of attenuate already, right? Attenuate means that the power of the receiver will be smaller than the power of the transmitter, right? I explained this content in like decibel content, right? So to understand P out over P in, if P out is less than P in, so this one will be less than 1, right? And then if you take a log, and then you can represent this one as the dB. So in this case, if P out is less than P in, the value of the calculation will be minus in the unit of dB. Okay, so this means the power of the receiver or P out of the system is smaller than the power of transmitting power. Okay, so this is the fact, we cannot avoid that. Okay, so as the definition, the signal loss strength, so strength here can represent as the power. On the other word, the signal is attenuated. So we cannot avoid this situation. Why I means that you can imagine that when you use your mobile phone and then you are very close to the base station, you can see a bar like to represent your how much you have the signal, right? I mean how strength of the signal. So you have like full bar of the representation of the strong power. So if you are closer to the say base station, so you will get high strength of the signal. But then if you move apart from the transmitter, this one will represent like you have a small strength received from the base station. Because of what? Because when you walk out, so the coverage area, I mean the distance, when this distance is increasing when you move apart, right? So of course the power will be decreased. Okay, so this is a fact. What I mean, so the attenuation happen all the times when you move from the base station. Okay, without consideration of the blockage, even it's clear environment. What I mean clear is that in terms of radio or wireless propagation, clear environment, or we call free space, means that the space or the environment that the transmitter and the receiver can see each other without the obstacle. There is no obstacle between them. Okay, so it's like you and the base station have a direct line of sight, direct path without any obstacle in between. In this environment, we call free space. Even in free space, okay, the attenuation occurs. Like I mentioned, if you move apart from the transmitter or base station, of course, the power will decrease. Okay, the signal loss strength at the rate proportional to the square of the distance. What I mean is that when you move out, the power will be with this ratio. Okay, so here the signal loss strength at the rate are proportional to the square of the distance. Okay, so if you move just a little bit, but the power decrease a lot within this rate, the square of the distance. Okay, and then in the real situation, we cannot avoid the obstacle. For example, if you are sitting in the class in HM building and the base station is just outside, outdoor environment, and your mobile phone and the base station have many things in between, right? There is a door, windows, building, right? We call that an obstacle, okay? With the blockage environment, with the obstacle, of course, the power will be absorbed. And then the power received with your mobile phone will be very, very low. Okay, so yeah, for attenuation, actually it depends on one is the distance and the second one is the blockage. Both type of attenuation limit the ability of receiver to capture and interpret the transmitted signal. This is a problem. And then for the second impairment or the problem, we call multipath fading. And actually the definition are quite similar with the interference, but actually they are different. Okay, so for multipath fading, it is the phenomenon that the desired signal and the reflected signal arrive at the receiver may cancel each other. Okay, so this is a situation of multipath. What you have is that, okay, this is you as a transmitter and you send the signal to the receiver. Then the receiver may not receive just only your signal, but receive, we can call a copy version of the signal actually. You see, because this is from the same transmitter. with these directions directly and with this direction, because this is a wave, right? This is the wave, like this is a transmitter and this is a wave, and it propagates into the air, right? Some part of the wave front may not coincide with the obstacle, but some part may coincide with the obstacle, right? For example, this one, it imping at this blockage and then go through the receiver with another direction. So with multiple receive signal at the receiver, if you take a look in time domain, so for the signal arrive directly, maybe it's very beautiful shape like sine wave, but in general, it's not like sine, but it composite signal. You have to understand composite, okay? You check it. And then for indirect part, I can say this is the yellow one as indirect. Okay, with indirect part, it arrives later. It may not like beautiful like sine wave. And then some part of the receiver, some part at the receiver side, it have to combine for every instant of time, for every signal it receives. Okay, so sometimes, for example, maybe here, this is the negative value of voltage, right? And then when it combined to each other, it's like maybe the output will be like very slow. Not slow, but very low power. Okay, so for this one, maybe it's very low. So what I mean is that when the receiver receives the signal more than one, it will combine or maybe cancel to each other. So you may have an experience that when you use a mobile phone in active call, you are calling, you're in the call, and then when you move a little bit, your friend's voice will lose or like just no voice. So it means that your mobile phone as a receiver can receive many signal, even from you as a transmitter. So actually, what multi-part fading here is mean like fade, like it continuously decrease the power of the signal after it combined from multiple signal. Okay, so the good thing is that sometimes, for example, here you see the yellow one and the green one here have a big power, right? And then if it sum to each other, it will be like very strong power. Okay, so the good thing is that some instant time, the power may be like increase a lot, but sometimes the power may be cancelled to each other. So this is a kind of fluctuation, okay, fluctuation. And we as an engineer don't like this one. Fluctuation means that this is very random. You study with me, right? This is a kind of random variable. You see, we can apply this one with this subject from math, okay? So actually this is a random variable with just a signal, okay, from only one transmitter, but at the receiver side, you can get original version, means the desired signal, or a copy version of this original signal. So this is not good, but we cannot avoid this situation, okay? With only one transmitter, it can make a copy version. For example, if another building there, and this is a wave, the same wave, right? And it arrived, coincide with, incident with this building and then reflect back to your, so it actually from the same transmitter, okay? And if I draw like the blue one, the receiver will receive 3 signal, okay, 3 signal. And then it will fluctuate a lot. And at the receiver side, it's very difficult to distinguish this, what actually the direct part and what is the the yellow one or the blue one. It's very difficult to distinguish it. But today I like to introduce you how to improve the quality of signal if you face with this problem. Okay. So this is multi-path fading. I repeat again, for multi-path fading, there is only one transmitter send the multiple version of its signal to the receiver. So it means that the receiver side will receive many signal from only one transmitter. Okay. Okay. So for the interference, what is it? It is the phenomenon that the similar signals share the same medium. Similar means not the same, not same. Okay. Similar signal sharing the same medium and arriving at the receiver simultaneously with the desired signal. So this is the representation of the interference. I better erase this one. I think. Okay, for interference, okay, so in this case, the receiver is only one, and receiver receive multiple signal from different transmitter. Okay, so the receiver here, of course, receive the signal from this wave, right? Both direct and indirect part. And also this receiver receive a signal with different transmitter. Okay, share the same medium means that in this case means same the spectrum range. Okay, so this is another transmitter and it propagates the signal also, right? And the receiver will receive more than one signal, of course. But then in this case, similar for multi-path fading. So at the receiver side, there are multiple signals and then they combine with each other. Then some instant of time, it cancel to each other, right? And sometimes it combine each other. So it gain a lot. Of course, in this case, interference make it fluctuation also of the signal. But please be noted that these two are different in terms of the number of transmitter. For interference, the signal come from multiple source, multiple transmitter. But for multi-path fading, okay, multiple signal come from the same transmitter. Okay, but at the end, I mean at the receiver side, it receives many signal, and we don't like it, but we cannot avoid it. Okay, sometimes it happens. For example, in daily life, you may have experience of interference. For example, when you have an active call, you are calling with your friend, and then suddenly you can hear another person's voice. So it means that another voice is from another transmitter, right? So that is a kind of interference, okay, because the signal are from the different sources, okay. But for the end of the situation, we cannot like avoid the fluctuation of the signal. And for the fourth one is the interception. Okay, interception means that it is the phenomenon that in the unprotected medium, so like the air, without encryption of your signal, the third party can capture the transmitted signal without permission. Okay, so this is like kind of, if you have to protect interception, you have to do more for physical layer. So after you do modulation, you have to do the encoder also. I mean, the signal should go to encoder to do encoding or ciphering or something that to make your signal more protect. Okay, this is an interception. And about the transmission part, as I mentioned in the previous slide, there are actually two main parts. One is called line of sight. Line of sight. Okay, let's try to hide. For the line of sight, it means that that is the part that directly transmit between transmitter and receiver. So if this transmitter, the base station as a transmitter and a mobile phone as a receiver, then the line of sight means that this is, directly transmit without obstacle in between. So you can observe here that this is a shortest part compared to other. So another part is called, actually we can call non-line of sight, a loss non-line of sight, or we can call indirect part, okay, indirect part. So the signal can propagate and incident with an obstacle and then reflect back to the receiver like this. This is a kind of mountain and this is a trees, building, right? With the same transmitter. In this scenario, actually this is multi-path fading. Multi-path fading means that only one transmitter propagates the signal, but there are several versions of the original signal. Okay, and the receiver can receive multiple signal with line of sight and non-line of sight. Okay, and then this is a mechanism of the propagation. Okay, there are three main parts. One is the reflection. From Snell's law at your high school level, I think you learn already in physics subject. It's about the reflection. So if the signal incident with a large obstacle and the plane is very smooth, the plane wave are incident on the surface with the dimension that are very, very large compared to the wavelength. And then the angle of the incident and the angle of the reflection will be the same. So this one is the reflection part. Okay. What I mean is that actually we cannot avoid the obstacle, right? But we can still receive the signal from the transmitter because even it incident or arrive at the building like this, but still we have the signal like have a different direction, but it's kind of a wave. So we can get the power for some certain amount of power. We still can receive the signal. And then for scattering, okay, the scattering happen at a small obstacle like a sign like this. So this is very small dimension, right? So if the signal, okay, the wave are incident upon an object whose dimension are on order of wavelength or less, so on order of wavelength or less than wavelength, then and cause energy to be redirected in many directions. So it means that it can generate a wave in many directions. So it's kind of scatter. So some power go to this direction, some power go to here, some power go to here. So it's kind of scatter. But anyway, this kind of mechanism still can provide us to receive some information from the transmitter. And another one is the diffraction at the edge. Okay, this occurs according to Huygens principle. I think you learned from physics already when you learn about wave. Okay, so I think you have heard this before. Huygens principle, what is it? So as it mentioned here, it occurs according to this principle when there is an obstacle between transmitter and receiver. Say the transmitter is here in front, another side of this mountain, and then you are in this cruise for your trip, then you can still receive the information, but the power of course will be smaller than the power you got from the original transmitter, because the diffraction here when it arrives at this edge of the mountain, this one, the edge of the mountain will act as a secondary wave. I mean the second source, the secondary source. So it means that it will act as a source and generate a signal. based on this source, and then the direction will change also. Okay, the secondary wave are generated behind the obstructing body. So what I mean in this slide is that we cannot get direct line of sight easily. It's quite impossible, especially in indoor environment. What I mean indoor environment means that most of the times in one day you spend your life in indoor, right? And then you use your gadget, you use your IoT device in your room, your house, or even in the school, right? In the building. So it's very difficult to have line of sight. But you can still receive the information from these propagation mechanisms. Of course, the power will decrease, right? Because it lost when it incident to the obstacle, but still you can get some power from the transmitting signal. Okay, so this is a real scenario of the propagation mechanism. We have transmitter here, okay, kind of high tower here, and this is quite, higher than a building. And then the receiver is here. And then you can see in this scenario, we can receive a direct signal because some part we still get the directly transmitting signal from the transmitter to the receiver. But some may incident with the edge, right? If it's the edge, and then the wave will go in another right direction, it's called diffracted signal. And some wave will incident into a big plane where the dimension is larger, much larger than lambda. You know lambda, right? Lambda means the wavelength. So it depends on the frequency that you operate. For example, if you use, Wi-Fi, the frequency you use is 2.4 gigahertz. Then you can calculate the lambda based on this frequency you use by using this equation, right? So if you know F, and this is a constant value of the velocity of light, meter per second, and then you can calculate lambda, okay? Then in this case, it will call reflected signal, okay? The receiver can receive the reflected signal. And if the signal arrives at the sign and the dimension is roughly same as lambda or smaller, then it's called scatter. This scatter can also send the signal to the receiver, but maybe the power is kind of like very small. But anyway, we can capture some power from the scatter signal. Okay, that is the impairment and how wave propagate and how can we receive the signal even there are some obstacle, right? And then we arrive here. Why do we need the spread spectrum technology? More consideration in the design of wireless communication. Most of the application, this is may not true for IoT, but it's true for like data broadband, or even cellular communication. This is true because most of the wireless communication have a goal to have a high data rate, okay, high speed transmission. When you playing game, right, you want very high speed and broadband, then you can like playing in real time, right? So most of the big application have a goal like that, have a goal of high data rate, even in multi-path fading environment. Okay, you play a game in your room, and your room is indoor environment, and you cannot avoid a multi-path fading. Okay, so you need the technique that can achieve the high speed while combating the multipath fading. So the communication theory that you already study may not enough. Okay, so there are things. I mean, the technology developed to achieve this one. I mean, achieve the high speed while the environment is very severe with the multipath effect or interference, and most of the technology used nowadays, I can say nowadays, you can see in the physical specification as I show you for example, Bluetooth or Zigbee or Wi-Fi. You will see the words of spread spectrum. One is the frequency hopping spread spectrum, and one is direct sequence spread spectrum, right? You have seen this word before. So it means that by using the general modulation is not enough, okay? In terms of IoT application, if you use the Bluetooth in your home, you cannot avoid multipath fading. Or in my case, I use the Bluetooth in a truck, which is very small area. So the wall of the truck is a kind of obstacle also. So it will lead to have a severe multipath environment. So by using especially PAN, personal area network, okay, you need this one, sure, for sure. And then you have seen this one, for example, for frequency hopping spread spectrum in Bluetooth, right? Bluetooth Classic and BLE. And you have seen this one in the context of Zigbee, right? So you see these two belong to the WPAN standard. And of course, not only modulation technique use, but also the spread spectrum use. And also you may categorize this one in the low rate, because this is IoT application, but what I mean here is about the high rate. So maybe this one is for WAN, wide area network, okay? Wide area network contains like cellular or like satellite, something like that. So we need this also, because even we use a wide area in outdoor environment, we cannot avoid building, right? Especially in Bangkok. Even it's small area, but we have very high-rise building and we cannot achieve the line of sight environment for sure. So this kind of technology are requested to use in this environment. Okay, so one is the spectrum technology and another one is OFDM. Okay, OFDM and latest standard of 5G use OFDMA. Okay, actually used in 4G already. So these two standards trying to help the quality of signal improve. Okay, so we cannot avoid the impairment, but we try to find a technique that help the signal have the higher quality. All right, so this one, this two is just representation of how the spectrum of these two technology. So if you see here, okay, this is the spectrum technology. Actually, if we don't use this one, we just use the modulation, we can calculate bandwidth, right? You can refer back to the previous handout. And for every modulation technique, you can calculate bandwidth. Okay. Then the bandwidth that you get from the modulation, we can say that this is narrow bandwidth, because if you take a look in the specification, most of the application or system have a unit of kHz. I mean the bandwidth of the existing system, okay? So if in the unit of kHz, we call that system as the narrow band technology. I will explain again why we need the spectrum, but this slide just show you what the spectrum of the technology will be. Okay, by using the spread spectrum, you can see that the power of the signal will be decreased. But what you will get is that the frequency will be larger. Okay, then if you calculate the area under the curve here and the area of the yellow, the orange or yellow one here, actually the power density are the same, because this is a graph represent what we call power density. So how much of the power dense respective to the frequency. So in this graph, you can see that the maximum power will be around the mean frequency here, right? The mean frequency here, or we can say the central frequency. At the central frequency, the spectrum will be the highest value, okay? And then for another frequency, the spectrum, the power will be decreased according to this graph. And by using the spread spectrum, the maximum power will be like compressed to be lower, but what we achieve is that the frequency will be wider. So what it means from this picture is that we can spend larger bandwidth compared to the narrow bandwidth. And there's some benefit of that. I will explain later on. But this one is a kind of spread spectrum. Okay, the power of the signal is still the same because the area under the curve is the same. So it means that we still have the power density same, but we can try to use a longer, or a wider bandwidth for transmission. There's a benefit behind that, okay, compared to narrow band. And for the orthogonal frequency division multiplexing, this is a kind of multiple carrier, right? If you take a look here, you have only one carrier frequency that send your data, right? But for this figure, it represents multiple carrier. Okay, for the first one, the red one is called the first subcarrier. The blue one is the second subcarrier, and the third one is subcarrier. This is make it wide also. The spectrum is wider also, and it combat with the multipath and interference environment also. Okay, we will study this later on after midterm exam. All right, but I can say that these techniques are used in current technology and also future technology. And actually it used from 3G, third generations already. It used CDMA for 2G, and it used in wireless LAN, which is using ISM band, and it's also used in IoT application also, as I show you in the specification for some standard like Bluetooth or Zigbee. Okay. So what is the space spectrum transmission then? Okay, so as I show you here, actually before the previous slide, in the spread spectrum system, the transmitted signal occupies a much larger bandwidth. So this is what it means. Okay. The spread spectrum radio can share the medium with other spread spectrum and traditional system in FDM format. So you may confuse that. I often told you that we have to use very efficient spectrum, means that the small bandwidth by sending a lot of data, right? But sometimes we have to to do pro and con. If you can send a larger bandwidth, but then the quality is better, you may choose this choice. And this is the one, okay? You try to avoid the impairment by using a much larger bandwidth, like in this figure, Okay, and then for the second bullet, it mentioned that for a wider spectrum, still it can work with other exist technology. So because originally is here, right? This is original bandwidth. And then after you do the spread spectrum, it become wider. So it may have the same spectrum of another system. For example, okay, if you, for example, this is 2.4 gigahertz, and then you do a spectrum, and then the bandwidth is much wider. And here it used for 5G also. So you may observe that some spectrum may overlap with each other. Okay, of course, it's overlap, but it can work at the same time without, with very small effect. Because if you take a look here, when I draw here, 5G without space spectrum is narrow band, right? So the power is high. Then by using the space spectrum, the power is compressed to be low power. Okay, so it can like send into the same spectrum, but have a little interfere, so that is acceptable. In this case, the power of 5G is much larger than the power of the spectrum signal. Okay, this is what the second bullet means. So after you do the spreading, of course, the bandwidth is very, very wide, and then it will overlap for other existing system, but it can work. Okay, and then this is just explain the evolution of the spread spectrum. Actually, it was first invented long times ago, Second World War, and it has dominated military communication application to, the objective is to resist to interference and interception, right? We have, I think you understand this context, right? In military, you have to like watch out the enemy, right? The enemy is a kind of interferer, right? And a kind of interception also. Then you try, the military sector want to like try to avoid this situation, try to avoid the interference and also interception, and then space spectrum technology was invented. But recently it was transmitted short for, as I mentioned, 3G. This used direct sequence space spectrum often in 3G and also for following standard like 4G, 5G also. And what, as I mentioned, it's used in WPAN and LAN. Okay, this is, this slide try to explain why do we need the space spectrum then. Okay, now I think you understand the concept of interference and multipath already. Okay, so in the traditional system, if the channel is distorted with the interference, or the transmission will be collapsed like this. Okay, this is your signal, the desired signal, okay, represent in power spectrum density, and this is your bandwidth, okay, and accidentally when you send a signal with this bandwidth, with this center frequency, then accidentally the interference come with the same bandwidth. Then in this case, your desired signal is lost for whole package. Okay, because it's crashed, it will be corrupt with each other. Okay, and you may say that, okay, it's corrupt, and then why don't we just transmit again? All right, you can transmit again, but without doing anything, you will transmit with the same frequency, right? Same carrier frequency. Then in your medium, your channel, interference still there. Even you do the retransmission, but still it uses the same frequency, and the bandwidth will be narrow band also. So you cannot escape from this situation, right? So what should we do? So it mentioned here that Since the bandwidth of the desired signal and the bandwidth of the interference are typically narrowband. Okay, in general, without doing the spread spectrum, as I mentioned, the bandwidth is the narrowband, and also interference from another source is narrowband also, right? We can imagine that, right? We just do the modulation by using the center frequency, and then suddenly this situation may happen. Okay, and if the signal is transmitted in the frequency of the interference, like show like this, okay, the signal, your signal is transmitted in the frequency of the interference, so the same frequency and the same bandwidth, the retransmission would not help. This affects the quality of receiving signal. Do you know why? Okay, of course, you send this only this signal, but along the way, this is from transmitter, right? This is from transmitter, and then the signal is propagated into the channel, okay? In the channel, you have the interference. Then it arrives at the receiver with this one, right? You send the desired signal with the high power, of course, and then suddenly you face with the interference in the medium, and then both of them arrive at the receiver. And it mentioned here that this received signal have a low quality. Do you know why? This is the reason. Because the signal to interference ratio of the traditional system operating with the frequency of interference become very low. Do you remember signal to noise ratio? Signal to noise ratio. What is it? What is it? We use this to what? We use this to evaluate the system. This is very important for our communication. How good is your system? So if SNR is have a big value, have like, so if SNR is high, so it means that the power, so this one is the power of signal, right? Compared to the power of thing we call noise, and here, noise in this term is the interference. So if the power of the signal here, you can represent it here, right? S compared to N, or say I here, interference. So if this happen, so it means that the signal to, I mean that the system have a low quality, because the received signal have like very is affected from the interference, right? Not only the interference, but this happened with the multi-part fading also. Because multi-part fading is just actually your signal, copy version of your signal, right? It is using the frequency of the desired signal, because it's your signal, but a copy version. So the frequency of your signal and also another version of your signal will be the same, right? So this maybe happen also, and the S to SNR or S to interference ratio is very low. Okay, then if you catch my point, if you want to make SNR bigger, what should we do? This is the point, okay? This one make the SNR very low, so we have to increase SNR then. So by using the spread spectrum technique, here is the transmitter side, okay? Okay, so the spread spectrum is a wideband signal that has a superior performance over the traditional system over on the multi-part channel. And it mentioned that it's available, reliable transmission in urban and indoor environment. It's just like to show the benefits of using this, okay? By using this technique, so we can have a reliable transmission, especially in urban, and indoor means that there is really fluctuated signal, right? Fluctuated signal. Because it's indoor environment, there's many signal arrive at the receiver. So the goal is that, okay, this is the transmitter side. What you have to do is your desired signal have to do the spreading of the spectrum. Okay, by doing that, you can observe that this is a transmitter side. Okay, after modulation, and then you send to the spreading. Okay, and this is a spectrum that you send through the air. And suddenly in the medium, you face with the interference. Okay, the interference is there, but you yourself protect by like spread your spectrum wider, of course, but you are okay to have a lower power, okay, for the transmitting side. So by using the spread spectrum, the power become lower, but the bandwidth become much bigger. And then, of course, it's still faced with the interference around this frequency band, right? In this band, it still overlap with the interference, but you can observe that the remain parts of this frequency and this frequency still available for the receiver. I mean, available means that no effect from the interference with this one. Okay, you got my point? Oh, we cannot escape from the interference. We do also with this interference, but still there's much parts remain for transmission of our signal. Okay, that is the concept. Then this is a transmitting side, right? And then imagine that these two blocks arrive at the receiver. Okay, these two blocks arrive at the receiver, and at the receiving side, the goal is that to have the spectrum density of the original desired signal with this narrow band, right? After this spreading. So what it means is that, okay, for transmitter, it have spreading and it faced with interference, right? With the lower bandwidth. And then the transmitter have a low power with a higher bandwidth. And then these two arrive at the receiver together. So with the interference, and then this arrive at the receiver. So at the receiver side, you have to detect the original one, right? Original one is that you actually have a desired signal like this, but by go through the spectrum block, this narrow band become wide band, right? And then at the receiving side, the objective is that you get this back. So you have to get this back. So what should you do? So you have to do the convert version of the thing you do at the transmitter side, right? So what you did is that you do the spreading. Then at the receiver side, you have to shrink it. If you make it n time wider, so you have to like shrink it n time lower. So when it arrives here, then you have to divide this one by the factor that you expand, right? And then you can get the same, okay? Any question? This is the desired signal. So by doing this here, it do with this also. So this interference arrive at the receiver also, right? And it will do this spreading also. But please be noted that this is the first time to do the spread spectrum. So what we did with this one is a factor of n, right? So this one have to do with the factor of n also for the first time of the spread spectrum. So it means that the interference spectrum will be wider n times. So this is what it means here. If you calculate the signal to interference ratio with this one, what you get is that this is very high, right? So the power of the signal is here and the power of interference is here compared to the system without the spread spectrum, you will get this one higher. You get my point? Right? This is the benefit of doing the spread spectrum. Of course, at the beginning, at the transmitting side, you try to make it wider. Of course, the power is small compared to another noise, of course, but also we just send this and okay, even the power is low, but we have some area of the frequency to accompany this information. Okay, it's very wide. Even it is still incident with the interference, but it still carries much part of the information. And then at the receiving side, you do the backward process by using the spreading. Okay, for the transmitter side, you do spread n time. So the receiver side, you shrink it n time. So you can get the original one. But at the receiver side, you have to do with the everything you get, right? You do the same process, and interference come also together with your desired signal. And then when you do this spreading, so the interference have to do also. Okay, so the bandwidth of narrow band of the interference become wide band, and the power become lower, much lower. Then you can calculate SNI to be very, very high. Okay, this is the concept of the spread spectrum. And okay, any question? Concept is very easy. Transmitting part make it wider, and receiving part make it short, the same as the original one. Okay, and there are two main techniques as I mentioned, and the spreader block is in between before or after modulation. Okay, this is actually what I explained to you like at the beginning of the course, right? There's many, some components. This is transmitting side, and it includes modulator also, right? If you have a signal and then you prepare for transmission, what you have to do is to demodulate. And then if you want to apply the spreader, you have to include this block either here or here, depend on the technique. And for the spreader, okay, after you do the spreader, it becomes like this, okay? So modulation will have like the desired signal, very, actually narrow band, but for after doing the spread spectrum, it becomes wide band. And for the receiving side, you have to do the backward process, okay? So you have to put the spreader here or here, depends on the technique. And of course, okay, this is just to explain the advantages of the spread spectrum. As I mentioned, it is a wideband signal and has superior performance over the multipass and interference channel. Okay, and we can say that by doing this, we can get a reliable transmission. Okay. And by using the spread spectrum, it can overlay onto bands where other systems are already operating, as I showed in the previous slide. And okay, it's we can call that spread spectrum is an anti-interference characteristic because it's not interfere. Actually, it's not 100% interfere, but interfere a little bit with a small bandwidth. Okay, and it mentioned that for modern communication, it applies for CDMA at the beginning step of using the spread spectrum, and also applying in unlicensed ISM band, especially in PAN. Okay, and there are two method for spread spectrum. One is frequency hopping and another one is direct sequence. And we will complete this one today, and we will continue with this one after midterm exam. Okay, so for today, what is frequency hopping? I explained a little bit at the content of Bluetooth already, but yeah, this is just go into a detail again after modulation, what happened like that. For frequency hopping spread spectrum, the objective is what? Objective is that we want to make a wide band, right? We want to spread out the spectrum. Then by applying this, the transmitter shifts the center frequency. Say, we can say the carrier frequency, because when we send our information is not fundamental frequency, right? But the frequency of the carrier. So, but the carrier have some bandwidth also. So we can say center frequency or the middle frequency of the carrier. Okay, by applying frequency hopping, the transmitter will shift the center frequency of our signal. Shifts mean like jump a lot, jump in many times. The shifts in frequency or frequency hops occur according to a random pattern that should be defined before transmission. Okay, a random pattern, this is known only the transmitter and the receiver. Okay, this is just a little bit of ASK. Okay, you have your input as a binary sequence, and you want to modulate with this carrier. And by using on-off keying in this ASK, right, you will have this modulation like this, and this is the bandwidth that you get, right? This is your bandwidth with the center frequency here. Okay, and this is what modulator do. What modulator does, right? You have a bandwidth like this, and then if you apply frequency hopping, for example, if we move the center frequency randomly among 4 different frequencies, then the required transmission bandwidth is 4 times, right? Right, because we move 4 times, then so it's like this. So this is your data, right? And then the spreader is after modulator. So originally your center frequency is here. And then by using this spreader, given a random sequence we call pseudo random sequence, it shifts from F2, F4, F1, and F3. So whatever FC is, it will jump to F2 with the same bandwidth as this. Okay, and then for the next packet, it jump again to F4, right? And then for next bandwidth, it jump to F1 and F3. So you can compare easily from this figure, these 2 figures, that without doing the spread spectrum, you can calculate narrowband, okay, with this equation. But after you jump 4 times, with different frequency, 4 different frequency, your bandwidth become 4 times of this narrowband, right? So this technique is called a spread spectrum technique because the spectrum is spread over the original band. Okay. And it can apply to analog and digital communication, but nowadays we apply primarily for digital transmission because everything, what any information we get is, we convert it to be digital before transmission because of it have more benefit than analog signal, right? So it's applied for digital transmission mostly, for frequency hopping spread spectrum. And this is a block diagram. Okay, so you do the traditional mode. If you use the digital mode, this one can be SK, FSK, PSK, higher order, right, for 8 PSK, like that. And then whatever technique you use, you go through this frequency hop. Okay, and then output here will be wider bandwidth. And for the second, okay, let's see for each. This is transmitter, this is what I mean. Okay, we have this one, this is transitional mode, and by using this random sequence F2, 4, 1, 3, then we can get a wider bandwidth. And this is called pseudo random sequence or code. Okay, and for the receiving side, you do backward, but the pseudo random will be the same. So what is the sequence you use in transmitter? You have to use it at the receiver as well. Okay, So whatever you get, of course, is the analog signal, right? Then you have to convert it back, okay, to be narrowband here, and use the same technique of modulation, and then you can get this one. Okay. It mentioned here that in digital implementation, the sampling rate, you remember this one? Sampling rate is the same as the sampling rate of the traditional system. What is the sampling rate? In what context we use sampling rate? So you remember like sampling, right? You have an analog signal and then you want to make it like to detect just some points at each time, right? And then you have a quantization level, right? And then you make it like a binary encoder. So this is a called digital analog to digital converter, right? So to make it like to detect from digital to the original analog signal, mostly same. So you have to have the sampling rate at least 2 times of the frequency of the information, I mean maximum frequency of it. Okay, this is a sampling rate. So it mentioned here that frequency hopping spread spectrum have the same sampling rate with the traditional system. So what it can imply here is that for hardware, we do not need to have like a high sampling rate, because if it high sampling rate, we have to do like improve the hardware to like available for to get a very higher sampling rate. So by using frequency hopping, you can observe that, okay, we just do the sampling before, and then we just use the traditional mode, and then we just jump the frequency. That's all. But for another technique we call direct sequence, we have to do something in front before we do the modulation, and it needs much higher sampling rate in that case. Therefore, a more complex hardware complementation. Okay, so this is the benefit of frequency hopping. We can make a spectrum wider, and the system still have the same level of the traditional system. Okay, no need to modify the hardware. Just have a block in the block diagram to generate the frequency sequence to let the frequency of the traditional mode to jump over. That's all, not related to the hardware improvement. This is an example of hopping frequency of hopping sequence of and frequency hopping spectrum. This is 8 hop, and this is sequence. X-axis represent time domain, okay? And the black bar here represent the package for transmission. And this is one duration to transmit one package. And Y-axis represent the frequency. Okay, so I repeat again, if you do not use a frequency hopping, we just use only FC frequencies, which may be just only this band. Okay, this is bandwidth in hertz, something hertz. But if we hop, we jump for every package. So you can see here, there is 8 hop for each package. For example, for the first frequency, for the first package, you jump into F3, whatever frequency of the carrier is. You jump to F3, and then you finish sending one package, and then next packet you have to send with the frequency of F5, and for the next packet you have to jump to F6 and so on. Okay, until F7, and then it go back to F3 again. Okay, F3 again, and then it jump like this. So it means that by transmitting our package, you need to have 8 times of this bandwidth, right? 8 times of bandwidth. Okay, so yeah, it's wider. And then if you take a look at shape of the signal, the power is lower. This is just a representation in terms of like easily understand about sending the package over multiple frequency. And in this example, because the carrier is constantly changed, the interference or multipath fading collapse only a fraction of the transmitted information. Okay, even we have spread like this, but suddenly the frequency of the interference is F4, for example. There are some signal. This is interfere. Okay, interfering signal have the same frequency of this package. This is what it means. So of course, these two incident with each other, and of course, this packet is lost. Okay, it lost. Can we do the retransmission then? Can we? Yes, of course. Why not? We can do the retransmission, and then the good things using frequency hopping is that by using the retransmission, we do not need to send with the same frequency that we face with the interference. For example, here F4 have the interference, right? But frequency hopping have like another frequency than F4, right? If it in sequence of other frequency, this packet that is already lost can be resent again with another frequency. So it means that, okay, so the incident of the interference and the lost package can happen, but we can retransmit with different frequency according to the sequence. So it means that at the receiving side, maybe this packet may arrive later, but it's okay because we can rearrange later. Okay, that's very good things. Okay, it mentioned here that this is a slow frequency hopping system where a long packet with a number of bits are transferred at each hop. So it means that it takes longer time for each hop. If you want to make it faster, you can make time slot shorter. So you can have a higher speed of the frequency hopping system. You can go back or take a look in Bluetooth system. There's, if I remember, there is 1,600 hops per second. You see, 1,600 hops per second. So it means that the package is very, very small, right? That's applicable because Bluetooth is for sending the information, which is very small amount, right? It sends information from a sensor, like in kilobit only. Then we just send it and then send it jump, and then we can do like faster hopping. Okay. So I think I explained this one already. We can retransmit the lost packet. Okay. So for the remains, I just want to show you the example of wireless system using frequency hopping. The first one is applied for wireless LAN. In the traditional system, if the channel is distorted with the interference, or the transmission will be corrupt. You see, all the transmission mean whole package, right? Because we use the same frequency as the frequency of the interference, right? Then any retransmission would not help. But for using frequency hopping, the packet transmitted during hop that coincide with the interference frequency would be corrupt, but we can retransmit it. Okay, and with this standard, which is Wi-Fi, use this concept also. And the maximum time for each hop is specified as 400 milliseconds. So like this is 400 milliseconds for each hop. But for the real transmission, it usually like something tens millisecond, as mentioned here. Okay, here. So the maximum time slot or maximum time for each hop is 400 millisecond, but the length of package is around 30 millisecond. So therefore, a package corrupted by narrow interference can be retransmitted during the next hop within 400 meter later, which is reasonable delay. So what it means here that even if it coincides with the interference, right? And then we can retransmit that packet for the following time of the time slot, which is only 400 millisecond. This is satisfied or short enough, like, okay, we can wait to get a packet from retransmission. And for dot 11, apply frequency hopping for wireless LAN. There are 78 hopping channels. So the frequency hop is 78 frequency. Okay, each separation by 1 megahertz. So one channel have 1 megahertz, and then it's spread until 78, right? These frequencies are divided into 3 patterns of 26 hops. So among this 78, it divided into 3 groups. And one group is 039, blah, blah, blah. And the second group is 147, blah, blah, blah. And the third group is 258. Why they do like this? This mechanism allows the installation of 3 access points in the same area without any hop collision, resulting in increasing capacity of the cell. Okay, I can explain this one like to let you imagine that, for example, for a special event, for example, the graduation ceremony, okay, everyone go to a big hall, right? In usual, we don't use a big hall, right? Very small people there. Then we can just using one access point, that's fine to be service for the people. But if there's a kind of big event that many people comes, and then we need to increase a number of users, okay? Increase capacity in this sense means increase the number of users, okay, without interference to each other. What can we do? By applying the frequency hopping. So for Wi-Fi, it mentioned that, okay, there are 78, then we can, the standard can like provide 3 groups, and then it available. It is okay if you have 3 access points in the same area. If this is a big hall, right? Usually we have only access point 1. Everyone in this hall can access to this access point. But then but anyway, by using the frequency hopping, every mobile phone have to connect with the access point with the same frequency hopping sequence, okay? And then, as I mentioned, for the special events, there's many people come, and then I want to increase the number of people, available devices that can access to the Wi-Fi. So I implement AP2 and AP3 in the same hall. If AP2 and AP3 use the same frequency pattern, of course, we cannot distinguish the network, right? We cannot distinguish a set of users who use access point 2 or access point 1 or access point 3, right? So to distinguish a set of users by using 3 access points, it mentioned that these 3 access points have to use different frequency hopping sequence. You know what I mean, right? So for AP yellow, okay, assigned to use this one. So every device want to connect to AP2 should send the information by jump the frequency from this sequence. And then If the user access to AP1, it should use to jump with this frequency. And if the device want to access to AP3, it used to jump to this frequency hop. So it means that you can increase a number of people or increase the capacity of this cell just to duplicate the access point, but choosing the different frequency hop. All right. So this one, this mechanism allow installation to access point without any hop collision, because we use different hop, right? We use different hop, so no collision between hopping sequence. Okay. Question? No. Okay. So for next, I just want to introduce you again. Actually, I just copy some slide from Bluetooth slide to represent again here that Bluetooth classic characteristic have like, okay, use 2.4 gigahertz and then use GFSK modulation, okay, Gaussian frequency modulation, and also use frequency hopping. Okay, you see here, Bluetooth use 1,600 hops per second, okay, and it uses pseudo-random sequence as well. And this is very interesting. Why frequency hopping used in Bluetooth? There's two purposes, two objectives. One is that, of course, original objective is that to provide resistance to interference and multiply effect, because Bluetooth is work well in indoor environment or can say that a severe situation, severe multiply. Okay, because it's short range, so it works very near, right? Originally for classic Bluetooth. And then, of course, there's multiply effect for sure. But by using frequency hopping, it can resist to interference and multiply effect. Okay. But for another objective is that it provides a form of multiple access among co-located devices. We have to highlight this one. Okay. Frequency hopping is used to distinguish the piconet, because what Bluetooth do is like this. Okay, I didn't show the piconet. Okay, I can draw here. You remember piconet is that, okay, you have one master and maximum to 7 slave, right? This is one piconet, but Bluetooth allow the device to be a member of another piconet. Say, okay, I have another one. Okay, so it means that this one belongs to blue network and also the red network, right? And this time, this device act as master in the red piconet, okay? And it have some slave also, all right? So it means that this one, the same device, can work with many networks at the same time with different role also. So when this device want to connect to this master, it have to connect using one frequency hopping sequence, right? Sequence 1. And then if this device want to communicate with each device in this red connect, so it have to use another frequency hopping sequence, say number 2, right? So what I mean is that frequency hopping is used in Bluetooth Classic to allow multiple access among co-located devices in different piconet. Okay, co-located device, that is what I mean. So the device can belong to many piconet. Okay, so multiple access means that this device can go through different network. Okay, and this one is used to distinguish between these two networks. Okay, it's similar with the Wi-Fi that I explained before. But for the Wi-Fi, this is not applicable, right? So the Bluetooth, so for the Wi-Fi, this one haven't happened. So the device have to like belong to only one network. But for Bluetooth, it allow one device to belong to many network. But the concept for communication is that if it works with this blue Piconet, it have to use frequency hopping sequence one, and it work with the red network, it has to use another frequency sequence. That's what it means. Okay. And okay, this is things I explained already in Bluetooth. And this one is frequency hopping. You use in Bluetooth because it uses frequency range from here, called channel 0, start with 24 to 02 megahertz, and the bandwidth is 1 megahertz. Then the second, another channel will be here, right, and so on. So in total, there are 79 radio frequency. Bandwidth is very wide, say 79 times, okay, of the original bandwidth. I think you understand the concept already about jumping in the package. And this is work with TDD. I explained already also, but I review again together with the frequency hopping. Okay, so here is the communication between one master and one slave. And you know, by transmission in classic Bluetooth, it uses TDD, time division duplexing. So it means that transmission and master to slave use another channel, and slave to the master use another channel with different time slot. So this is time division duplexing. Okay, not only that, because in general, if just only TDD, it uses the same frequency, right? Same frequency for every transmission. But for now, for Bluetooth, it's not, because every time that's sending the package, the frequency change also. You see? Okay, so it mentioned here that TDD is used to prevent the crosstalk between transmit and receive operations, and it take place different time slot and do different frequency hop. So by using the different frequency hops like this, for master sending with this period, right? When master transmit, slave cannot. This is the way that TDD works, right? It's not real time, but there are two channels to transmit between master and slave. Okay, if master want to transmit, slave cannot. And in this figure, it mentioned that master use frequency with K1. So say F1, okay, transmit to the slave by using this period, 6 to 5 microsecond. And then after that, slave want to transmit back, okay, with the different time slot and different frequency also. Okay, say this is F2. So you see this one and this one are different. This is aside from what? Aside from the pseudo random sequence. Random sequence, okay? It may be, I don't know, depends on what system assigned. But it just mentioned here that this is different frequency for every time that the packets are sent. All right? And this is just mentioned that for Bluetooth, it can be used, I mean, it can send the multiple packet at a time from multiple slots, because maybe the packet, I mean, the data is quite long and it want to transmit at a time. It's possible. So for example, this is general version, right? So it used to send one packet at a time. But if you want to send multiple packets, say it's allowed to send 3 and 5, why not 2? Can you answer? Why not 2? Because by using TDD, you have to allow another device to send back, right? So if you are a master, you send for the first slot, and then you have to wait this slave to send back for the second slot, and then you as a master send for the third slot, and so on. So if you want to send 3 at a time, it's possible. Okay, you send 3 times 3 packets, but please remember that this one is the same frequency. And then another one, I mean, the slave in this case will send the packet for the next frequency, not go back to FK plus 1. Okay, because it radio remains at the same frequency until it's finished packet like this. This is defined the frequency already. So if you send 3 or even 5 for FK, then the slave can send as the same frequency as defined before. In this case, it's not FK plus 1, right? But it's FK plus 5 for send back the information. Okay, so this is application of frequency hopping in Bluetooth. So that is all for today. Any question? No, no question. Okay. มีคำถามไหมคะ